Hi, my name is Nicholas Stagg, and my final project for Introduction to Material Science is going to be an overview of the shape memory alloy nitinol. So, introduction. What is nitinol? Nitinol is a near equiatomic alloy of nickel and titanium, typically composed of about 55 to 56% nickel. Discovered in 1962, the name nitinol comes from its origin at the U.S. Naval Ordnance Laboratory. What makes nitinol unique is its ability to exist in two distinct crystal structures: the high temperature austenite phase, which is cubic B2, and the low temperature martensite phase, which is monoclinic B19. The reversible transformation between these phases gives nitinol its two key properties: shape memory and superelasticity, making it indispensable in applications such as medical devices, precision actuators, and aerospace components. So nitinol is produced through a multi-step process. First, nickel and titanium are carefully melted together, maintaining the exact atomic ratio. After solidification, the alloy undergoes various heat treatments to set its transformation temperatures and stabilize the structure. Mechanical processing, such as rolling, drawing, or extrusion, is used to shape the material, and superelastic or shape-setting treatments are applied to achieve specific properties. Finally, a final heat treatment fine-tunes the material's transformation temperatures and mechanical properties. So this table summarizes the key properties of nitinol. I'm not going to go into each one independently, but I think it's pretty cool to note that the yield strength for austenite is 560 megapascals, and the yield strength for the martensite phase is 100 megapascals. That difference is pretty significant. I think it highlights the dynamic characteristics of this alloy. So this slide shows the binary phase diagram of the titanium nickel system. The x-axis represents the nickel composition, and while the y-axis shows temperatures in degrees Celsius. The green region, where the titanium nickel intermetallic compound exists, is critical for nitinol formation, which occurs at around 50 to 51 atomic percent nickel. As the temperature increases, nitinol exists in the austenite phase, which is cubic, and upon cooling, it undergoes a phase transformation to the martensite phase, which is easily deformed. This reversible transformation is what enables the shape memory effect and superelasticity. So this slide delves a little bit deeper into the phase transformation of nitinol. At higher temperatures, as we just talked about, it exists in the austenite phase, and when cooled or under stress, it transforms in the martensitic phase, characterized by a distorted monoclinic structure. This transformation is crucial for the material's shape memory and superelasticity properties. So key temperatures such as A sub S and M sub S mark the beginning of the transitions, and A sub F and M sub F mark the end of these transitions. So now that we've talked about the phase diagrams and just gave an overview of what the austenite and martensite phase is, I wanted to go into some 3D models of what this looks like. The austenite phase has a B2 cubic lattice that's stable at higher temperatures, and it's pretty rigid structure, so it's able to remember the material, and this allows it to remember the material's original shape. On the other hand, the martensite phase, which forms when it's cooled, has a monoclinic structure. The distortion in the lattice allows the atoms to shift slightly under stress, making the material flexible and reversible. These atomic reconfigurations underpin the shape memory and superelastic behaviors of nitinol. Now that we understand the background of nitinol and why it does what it does, I wanted to go into some current and emergent applications. So its unique properties are widely used in the medical field, such as self-expanding stents that expanded their predefined shape once in place, and guide wires that can navigate through tight and complex pathways. Orthodontic devices such as braces take advantage of the shape memory effect to apply consistent gentle pressure to the teeth. Nitinol also has applications in neurovascular devices, automotive systems such as adaptive grow and lower systems, and even in crash energy absorption due to its superelasticity. In all of these, nitinol's ability to undergo reversible deformation makes it an invaluable material in aerospace, the automotive industry, medical industry, and beyond. To conclude, nitinol's ability to transform between the austenite and martensite phases enables its remarkable behaviors like shape memory and superelasticity. These properties are key to creating reliable and lightweight components used in a wide range of industries. Though challenges like cost and fatigue life remain, ongoing research into surface treatments, additive manufacturing, and alloying strategies are addressing these limitations. As we look to the future, nitinol will continue to play a crucial role in the development of advanced materials and technologies. Here's my works cited. Thanks a lot for listening.